Sorting. It is one of the most fundamental problems in computer science. We take a jumbled mess of numbers and we bring them to order. We know there are slow ways to do this, like bubble sort or insertion sort, which take big O of n square time, and we have fast algorithms like merge sort or quicksort, which operate in big O of nlogn time. But have you ever noticed that we never seem to do better than nlogn? Is it just that we haven't found the right code yet? Or is there a fundamental universal speed limit stopping us? Today we prove exactly why you can't break this barrier. To understand the limit, we first have to understand the scale of the problem. If I give you an array of n items, how many possible ways could they be arranged? For the first slot, we have n possible choices. Once that is picked, we have n-1 choices for the second slot. We continue this pattern, n-2, all the way down to the last item. Mathematically, the total number of unique orderings, or permutations, is the product of these choices. This gives us n factorial. To sort an array, your algorithm must be able to distinguish between every single one of these possibilities to find the one correct sorted state. So how does a computer navigate these n factorial options? In a comparison-based sort, it asks questions. Is A less than B? The answer is either yes or no. Each comparison splits our universe of possibilities in half. Let's zoom out. The height of this tree, h, represents the worst case number of comparisons the algorithm performs, essentially its time complexity. Here is the key. This tree must have at least one leaf for every possible permutation. If there are fewer leaves than permutations, there is at least one input case the algorithm cannot sort correctly. Since a binary tree of height h has at most 2 to the power of h leaves, we get this inequality. 2 to the power of h must be greater than or equal to n factorial. Solving for h, we see that the time complexity must be at least the logarithm of n factorial. So we know h is greater than or equal to the logarithm of n factorial. But how big is that logarithm? It's the sum of logs from 1 to n. Visually, it looks like the area under these bars. We need to find a lower bound for this. Let's be aggressive. Let's throw away the first half of terms. They are small anyway. For the remaining half, from n over 2 to n, every single term is at least as large as log of n over 2. We have n over 2 terms. This rectangle represents our lower bound. When we write this out, we get n over 2 log n over 2. Through logarithmic rules, this expands. And mathematically, this simplifies strictly to lower bound nlogn. This proves that log n factorial grows at the same rate as nlogn. So here is the logic chain. There are n factorial permutations. Any comparison sort is a binary tree with height h. That tree must fit n factorial leaves, meaning 2 to the power of h must be greater than or equal to n factorial. Therefore, the height h is mathematically bound by nlogn. This is why a linear comparison sort is impossible. It simply doesn't provide enough information bits to narrow down n factorial possibilities. The shaded region represents the impossible zone. No matter how clever your code is, if you rely on comparing elements, you cannot breach this curve. We haven't just failed to find a faster algorithm, we have proven that one cannot exist.